let's get started. First, the exam will be next week. Will be two groups, one on Wednesday, one on Friday. Okay? And in order to, well, be honest, even though I said I don't care, I don't use the Zoom link, but sometimes it really bothers me when I see people's answer, especially, 3 or 4 people. The Excel format, the location for random number, for everything's exactly match. It make you wonder, how likely, and for me, fairness is important. So here are the 2 things I would like to do for the exam 2. First things first is that the TA will email you the exam problem. So you can tell there are some minor changes in the exam problems. And the second thing is that, for the random number used for, the error term, this is what the TA gonna give you is that, we'll have, your student ID number or your name. So, 1, 2, 3. Well, I guess use name is safer, right? Which way is easier? Copy their name and, well, either we'll use your name or your ID. Okay, so this is your name or ID for each one of you. So 1, 2, 3, 4, 5, 3, 4, 5, 5, 6, 7, 8. Huh? It happened again. Sorry. Okay, so you will have your name and so on here. Okay, and then after that, we'll give you a set of random number, and the random number will be locked. Okay, so say we have 16 random number, or I don't know how many random number we'll have, but basically said here is the set of random number you use for your exam. That way, everybody got a little bit of sequence differences, but the TA can still grade the whole things accordingly. But the logics is kind of like this, shuffle a little bit. And then the random number add in for you is kind of like your number shouldn't be the same as other people's number. And you guys can see it. We're going to just give you the sheet and say that here's your ID and here's the random number you have. And if you have extra time, you can play with other people's random number. But I don't believe, yeah?
So we're going to be adding that random number into everything we do for the exam?
Yeah, just like exam 1, except this time I give you the random number to be used. And to be honest with you, I've been in this business 30, 40 years. Guess what I even encountered before? I have this simulation class, okay? I have 3 students sitting in the back. This is the old days without the internet. Okay, the 3 students, they synchronize their head movement. Look up, look down, look at each other, make sure they can find me. And guess how I proved they cheated? They have exactly the same random number. So I'm just kind of like, well, you show me you can repeat the random number sequence. It's mission impossible. Yeah. And, well, I'm not, trying to play tricks here. This is no fun. But I need to maintain some fairness. You guys agree? Yeah, I just cannot let people, do whatever they want. The purpose of this still, you learn, so you can do something. Not random number is nothing. Okay. So everybody understand? There will be your ID and then the number you use. So we know you have to. Yeah.
So are these going to be sent out? Just to clarify, so we're getting our own test before, like, at exam time?
Yeah.
So it's gonna be like emailed to us?
Yeah.
Okay, so is it, can we do like a test email just to make sure everything goes through so we don't run out of time before test day?
Okay, yeah. And actually,
We can like schedule emails to go out.
yeah, the other way we can do this is when we broadcast the in the test, we just say that, okay, so and so, please use exam problem set 1, or use exam problem set A, problem set B. What I'm saying is that I'm basically tell you guys up front that this is the way how I minimize the potential, copy paste cheating mechanism. This is my mechanism to do that. Okay, I just need to make sure that you guys know that, hey, you have your own set of exam problem, your own set of random number. Please follow that accordingly. Okay, yeah. There's no, dirty tricks on anything like this. Okay. Next. On the this is only for grad student. Okay, grad student. Because our undergrad student in our curriculum development, they have their 2110 Python-based sophomore projects, and then they have 3110 junior project, and then they have 2-semester senior projects. So they have projects. And for the graduate students, you have no project and suddenly just one capstone project. So I need to give you guys a projects, okay? And of course, the two part of the material, we're gonna, basically your projects, okay? You can do 2-way factorial design, 3-way factorial design, fractional factorial design. Excuse me, I don't care, okay? But, what is important is, you need to, at the end, come up with your regression, ANOVA table, and so on. And another thing is important. Don't worry, I have my booster shot. I have my 3rd shot of my COVID. Just, I've been talking too much today. Okay. On the factorial design ANOVA table, the material I covered today, all the legal tests should be in there for your documentation. But how am I gonna evaluate? For the first part of the project, should we find data set online or should we perform an experiment? I would say that you can do it either way, okay? And the second part, if we can get a data set online, we must apply DOE principle to analyze the data, yes. Okay, so you have to show me your degrees of freedom, and then you should tell me, what are the effect, main effect, two-way interaction, things that you would like to investigate. Okay, are there any restriction on the software? No. If you said you don't want to use SAS, you want to use R, you want to use MATLAB, go ahead, as long as you give me the documentations. I can look at that up and be honest. What do you guys think about Excel for experimental design? It's pretty decent, right? You see what you get. You get what you see. Okay. A project poster, basically you can consider this. If you can put the project like a 16 slide, first slide introduction, second slide, and then you can easily build you guys know how to print slides into 6x6 matrices, right? Do you guys know how to print them into a PDF file? Yeah, and then just arrange them that way. And why I like to have a poster also at the end is that some of the good poster, you guys seen it around our buildings. From time to time, I'll print them out as a decorations when we have visitor, parents or from other school. We show, oh, here are our students' work, okay? And you can have a clear documentations, and I have people done it this way. Slides, and PowerPoint, you can write down a lot of argument as descriptions underneath, and you can do it that way. So, or you want to come up with another Word document to describe what's in the experimental design, fine too. For me, what is important is you have a very clear logics. Here's the evidence, here's the things. How are you going to express that? Guess what's my view? As concise as possible. So in other words, is that do you think you get more grade if you have 16 slides rather than 9 slides? You write 25 pages than 5 pages? No. But so I don't like to see a lot of yada yada, especially if you can copy paste from Wikipedia. That's wasting, everybody's time. But if you can write it to the point, and that's important. Okay. I probably explained this to you before. When you work in the real world, you would like to have your Christmas bonus, right? And what's the most important thing for you to talk to your boss is never give him a long essay. Always just multiple choice. Here are 3 options. Here are 4 options. And then what are the pros and cons? And what are the benefits? How are you going to prove your success? That kind of to the point. Okay? We want to investigate A, we want to investigate B, and here how we're going to do it. Okay? And for final class presentation, there won't be any online presentations needed. So just, have your documentation and have your PowerPoints done. Yeah, and the slides for the presentation and the poster are actually the same things. You guys follow me? So if you have the slides, you have the presentation done. I'm not asking you to do extra work, okay? And originally I planned to, have let's show our presentation day, and I don't think we have time this time, okay? So I'll probably just, at the end, broadcast everybody's poster and let everybody see the poster, okay? And the evaluation scheme, of course, your F-test, your ANOVA should be good. P-value should be clear, so you don't make mistakes in your statistics. And the second part for me is the significance. So what? Who cares, right? Yeah, you don't want to tell me. No, for example, someone's done a sushi experiment or done a popcorn experiment. At the end, you want to tell me that, so how to make the sushi better, how to make the popcorn better, okay? And that's very, very important, okay? And the things actually I would like you to write, usually at the end or at the beginning, is what do you consider, here is my key finding, I've done this so unique, so good, you should give me an A for my project. One simple statement is say, here we go, this is what I've done, different from what you cover in a class. And this is the science that I find. Usually that's one simple statement is yeah, where is the unique part of this whole thing? Hey, how many of you seen the 007, the new movie? Yeah? You like it? Really? Okay. For me, I look at the whole thing is that which part is unique? I haven't seen before. And so maybe I'm too critical on James Bond, but here's the argument I have about your senior project is that at the end, if you follow all the mechanism and get it done, including the mechanism I'm going to talk about today, you're good, okay? But what I'm saying is you really want to impress someone with A+ term projects. Focus on, here is the unique things I need to find. Okay, now let's go to the stuff I need to cover today. Okay, in the old days, I actually talk about this at the very, very beginning of the, probably second week of our class. But now I tend to move to the very end. And what we call them is multiple comparison. So if you look at the lecture notes, at the very, very beginning, we have 4 treatment experiment, right? And then we turn the 4 treatment, can turn into blocking or turn them into, what do you call that things? Latin square or factorial design, agree? And here's the things, okay? If I have A1, A2, A3, 3 treatment, what will be your questions? Which one is good? Which one's the best? Which one is the worst? Are there significant differences, right? And in your Stat 101 or, well, your first stat course, they call it what? Pair comparison for t-test, right? They can do that. So in experimental design, the same things. I can have 3 treatment here, and of course I can have B1 and B2. So if I do that, I can compare A1, A2, A3 and say which A is best. And I can also say which B is best, right? B1, B2. Now, but can I combine the 2 together and have this A1, B1, A1, B2, A2, B1. So if I treat it that way, then the multiple comparison is how many? Rather than 3 treatment or 2 treatment, we can treat them as 6 treatment, right? And then for multifactorial design, 2 to the 5, that we can say that rather than saying, A effect, B effect, we can say that there are 32 different treatment. We want to say which combination is the best. Agree? So the whole things, okay, what we're going to do today is so-called multiple comparison. Okay? And my way of saying that is that find your champion. Okay? Find your beauty queen. Find the best. Or find your worst. Okay? End of the story. However, put that down, okay? It's not legal to talk about multiple comparison unless you know that the ANOVA table says that A effect is significant, B effect is significant. If A effect is significant, then you said that, hey, then which A is better? B effect is significant, then you can ask which B effect is better. If A effect and B effect both significant and their interactions usually is significant, then you say that, okay, so now I would like to know what kind of compositions is better. Then that makes sense. You guys follow me? So in other words, the ANOVA table, and this could be in the exam, okay, is if the ANOVA table say there's no effect, and you fall into my trap and say that, hey, do a multiple comparison here, and you start doing a multiple comparison on an insignificant effect, what does that mean? You're already using the ANOVA table saying the distance, okay, are so close together, I cannot tell them apart. And if you cannot tell them apart legally, can you say which one is better? This is wrong, right? Logically. So just remember, the sequence of the multiple comparison only happen if your ANOVA table say there is a differences to show. Okay. And here are some of the tests people usually consider in a, oops. Okay, so let's just follow the procedure. So experimental design, first step, randomizations of the sequence, and then find a central station, find a subway station or different treatment, and then ANOVA said, oh, it's significant. And once it's significant, then we need to start evaluating the differences. The first thing you can evaluate the differences is what we call assessing the independence. Here, let me show you one example, is that if my error term, okay, say I run an experiment, here is my first observation, so this is my run. Okay? And, you know, I don't know, this is a two-way factorial, three-way factorial, and let's just say that is a two-way factorial design, a 5x5 design, or a 32-run design. Let's just say that I have a 32-run design for 2 to the 5 factorial design. So I have 32 observation, agree? Okay, and if the 32 observation, okay, they're showing this, the error term, okay, E, the error term, okay, is something like this. Oh, what did I do? Okay. If the error term go run by run, look like this. Okay, up and down, up and down, up and, well, actually this one is wrong. Guess why this error is wrong? I simulate the error is wrong. Why the error term here is wrong? Can you have always positive error? Half of them should be negative, right? So, okay, now some positive and some negative. Okay, now this one, you know, I use random number, so you know it doesn't really relate to each other. But if, okay, say every time I have a random number, okay, and then I will use my previous observation, error term divided by 2. Okay? Now, can you guys tell? It's drifting. So in other words, is that my current random number got something to do with my previous random number or my error term. So I can do this not so bad. I can just say that the previous random number, I will remember 20%. And then my current random number will be 80%. Okay? And if I do that, oops.
You did times 2, not times 0.2.
Huh?
D2 into...
Oh, times 2? Oh, yeah. Okay. So, you know, there are some cyclic going on. So, no matter what, if, okay, the error term of a regression or a ANOVA table from the Central Station subway station, always my current random number got something to do with my previous random number, then it's not completely IID, right? Independent and identical. Or I can put it the other way around. If the random number later on depends on the previous one, you want to be the first one, right? Or sometimes it's the opposite way, right? In the Olympic game, or if you're an Olympic figure skater or ski jump, would you like to be the first one? Do you want to be the first one jump? Two-part, right? The judges usually, even they see the best jump, they don't want to get perfect 10 because they want to reserve some space for the future. The second part, okay, maybe the weather, the wind, the snow, the environment got some parameters hard to tell. So let other people jump first, at least you can observe a little bit. So be the first one, sometimes got advantage, sometimes got disadvantage. So again, you don't want to be the first one or the last one. And scientifically, can anybody give me an example that sometimes our error, kind of like residual from the previous observation, how could that happen? Anybody? In your physics, chemistry, biology 101?
Like a mistake you would make that would, or just
could be mistakes. I didn't say that good. There's no value judgment. I'm only saying that how could that happen? That your current observation got something to do with your previous observation.
I guess, like you said, in chemistry, for example, if you were measuring something, clean your instruments of measurement on it.
Good job. Yeah. A lot of time cleaning procedures. Okay. I told you guys I worked for Liberty Mutual before, the insurance company. We tried to figure out detergent for restaurant because some detergent cleaning causing slips and fall. And we try to figure out what kind of solution is good, what kind of solution is bad. But when the lab experiment coming out, in the first run, we rejected. Why? Because it's highly autocorrelated. Why? Because when they come up with the first batch, they should clean, steam, basically wipe out everything from their previous experiment before they run a second one. But if the cleaning is not clear enough, then you're in trouble, right? And epidemiology, same things. A lot of time they did some surgery or certain procedure. If they don't recalibrate their equipment, then there are memories from the previous one. And that will be another problem. And so on one hand, we say, oh, completely randomized because we want to be fair. But the procedure itself could carry a lot of error term. So the way how we do it is this way, okay? So here are 16 error terms. You copy the error term and paste it down. Okay, so let me do it here. I actually don't need to copy the second column. You just copy the first one and said, okay, here are the total error terms I have. Okay. And then this is my 16 run error term. You just paste one column down. So you always calculate the correlation coefficient of your current error versus your previous error. And so if these two error terms, the correlation coefficient, okay, of my current versus my past. Oh, by the way, you guys know why, say, I have 20 observation, I only have 19 pair, right? Because you switch one. And then once you calculate the correlation, you basically said that, is this highly correlated or not highly correlated? And so when you've done this, okay, you basically calculate the assessing the independence by using EIJ in this, okay, and anybody? What? Okay, and the test, there's a name for it. It's called Durbin-Watson test. Okay, and the Durbin-Watson test basically is you can look at autocorrelations and like one autocorrelation, and you will like these things. Okay, as little correlated as possible. So in other words, autocorrelation, the number should be very close to what? 1 or -1. If you have autocorrelations, like 1 autocorrelations, okay, very close to 1 or -1, that's good news or bad news? Huh?
Doesn't mean that they're highly correlated. Right?
If they're highly correlated, that means that your instrument recalibrated well or not. Yeah, so whenever you do an autocorrelation, you want a number as close to 0 as possible. And the second thing is that the larger the number of run and increase, the variation should decrease, getting smaller and smaller. So Durbin-Watson basically said that, okay, how about let's just use the differences between the two divided by the sum of square of all the error term, and this number need to be less than 1.7. And if it's more than 1.7, you're in trouble. Okay? And this is the test for independence. Okay? And for most of the time, do you think your boss care about this? Hey, is your autocorrelation good or bad? Durbin-Watson good or bad in your report for any design? Do you think your boss care or not? Usually, they don't care. They just care, hey, did you find a significant one so I can use to do something? But if the one he likes is not showing up, he said, hey, A effect should be significant, or A-B interaction should be significant. And for some reason, your ANOVA table showing, no, it's not. Guess what will be the first things he will use to defend his gut feeling? Double check the cleaning procedure, double check the Durbin-Watson, make sure that you run the experiment the proper way. You follow me? So a lot of times, this is important is, yeah, I call it a scapegoat time. Try to find a scapegoat. Hey, we didn't find the things we want. Somebody must have made some mistake somewhere. Your boss will say that, oh, my gut feeling was wrong. And the thing is that he probably will say, show me the Durbin-Watson. And if your Durbin-Watson is big, then he will say what? Something's wrong there, right? Okay, next is called test for equality of variance. This is called BARLET. Again, this is a legal document. Usually, you don't see this in the main text of your experimental report, but it's in the appendix. Okay, so why we want to test and say that I have 4 subway stations or 9 different, 3 by 3, 9 different treatment. I want to test every subway station have equal variance. Anybody? I would like to have some interaction here because this is all about legal. Okay, young lady, your turn. Why we want to see that, say I have 4 subway stations. I want to see all 4 subway stations, the variations are equal. Why we want to do that? We want to say subway stations are higher or lower. That's our experimental design, right? But when we try to say that, okay, we want to say those distance compare with what? Sum of square of your subway station or treatment over sum of square of your error term. And so you want all your error term from the same error distribution, right? So in other words, you don't want to have one subway station, people commute a lot, and the other subway station, people doesn't commute much. If that happens, what does that mean? The experiment got some setup there, right? It's not a fair experiment. So the things we did here is, again, figure out the error term, okay? And then we would like to find the range, okay? So what is the range? For example, the largest number minus the smallest number for every subway station. And think about it this way, okay? If one subway station, the variation is got a very, very large range, and one got very, very small range, they are not equally ranged. You probably will say that, well, one subway station travel more than the others. So first, figure out a range. Second, okay, find the average of the range. Okay, and then using the D4 value times the range. Okay, and that way we'll say that, oh, on average, 0.03 for 4 observations, the value should be at certain value. So it's 0.3 times 2 is 0.68. And so if the range you have for any one of them is beyond that reasonable local commute. So in other words, is that for 4 subway stations with the travel range on average 0.3, you know that there are randomness. So some travel more, some travel less. But at the end, okay, nobody should go beyond 0.68. If you go beyond 0.68, means what? Hey, there's one subway station travel too much. Then if you see that, you know that something is fishy. Okay? So this is another smoking gun we use to talk about the, yeah. Did I share with you one of the tests I did when I worked for Liberty Mutual? Is, you know, if you go to a lot of major hospitals, a lot of times they have this emergency room. And outside the emergency room, you see people, guys in suit, 3-piece nice tailor suit, giving business card out. You know who are they? Outside the emergency room. Lawyers. And what they're trying to do is, oh, you got injured? Is workers' compensation related? Hey, I'll help you. Sue the company and get the money. And a lot of times they not only tell you what to say to the doctor, how to fake their pain and stuff. Okay? And one of the things we did was about limping. Of course, you know, the legal, they hire investigator, videotape. You said you have back problem, you fall on your back, and then they videotape your, you know, playing tennis without any problems. Then that's the good piece of evidence to show you, to say that you're cheating for money. The other one is they teach you how to fake limping, right? Oh, I injured my ACL, my knee, so I limp in certain way. And what we did is we put an EMG sensor. EMG is like EKG or EEG, but not listening to the brain waves or the heartbeat. We listen to the muscle tone. So when you walk, your muscle fire in certain sequence. Okay. So when a lawyer teach the guy, say, okay, limp this way, and said you slip and fall in the garden while you're taking care of their whatever in the lab. So what we did is we basically said, okay, in the court, showing the record, okay, walk forward. So they limped, right? Obviously, they hurt themselves. Okay, UPS should hear this, right? And so then we asked them, okay, walk sideways, limp sideways, and limp backward. Guess what happened there? Most people, if I said, oh, you need to co-activate your quadriceps and your hamstring at this timing to show that you have a very stiff knee, they know how to do it. But the minute we turn them around and said, okay, walk backward or sideways, guess what happened? They forget the timing. So now we can show the signal to the court and say, he said he injured. But look, suddenly it's a miracle. They can walk with the right timing to fire the muscles again. So what I'm trying to say here is the same tricks that a lot of times we say that, okay, show me what is a reasonable expectation. And then how come this is beyond reasonable? Okay? Yeah. So even on the legal testing for all the lab projects, a lot of time to prove something is there, it's hard, right? But to disapprove and say something is fishy, how much evidence do you need? Just one. You only need one in saying that, well, if this is the case, how come you see something different? One more, okay? This is probably the interview questions people will ask. Okay, how many of you ever heard, get, brainwash? P-value need to be less than 0.05 to be significant. How many of you believe that is the case? P-value need to be less than 0.05. You heard that, right? Alpha is 0.05. Where is that coming from? If you want to work for Liberty Mutual and I'm the one said that I'm sitting in to interview you, okay? If you do it right, I give you a 6-figure salary. Well, of course, live in Boston, that's nothing, right? It's too expensive there. But how do you know you're doing the right things?
So 0.05 is a 95% confidence.
Yeah, so what does 95 confidence interval means?
With 95% of the time, we're saying that we're accurately rejecting the null hypothesis when we're supposed to.
Okay, so one way you can talk about it is this, okay? I told you I have unfair coins. This coin always give you head, no matter what. You toss the coin, head, 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 19 head out of 20. Do you think the coin is fair or not fair? Probably not fair, right? So this is based on the so-called 20 questions argument. Okay, head, 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 then something's wrong. Okay, and in the old days, I call it a KGB argument. You guys know what's KGB, right? The secret Soviet secret police. Okay, did you do it? No. Did you do it? No. They punish you until sooner or later you start saying yes, 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 right? And so what is science here? There's no science. So if you're designing a spacesuit for NASA, okay, and then this thing's once lift off, there's no return. Do you think 0.05 is good enough? You probably want to be 0.01, right? 1 out of 100. Well, you want to be 1 out of 1,000. Your p-value could be much, much smaller, okay? And then if I'm talking about, hey, figure out if your girlfriend or boyfriend really like that restaurant. Should we go back again? Okay? Then, you mess up one date on the restaurant. It's no life and death situation. Your p-value could set up as 0.25, right? So what I'm trying to tell you guys is that don't get hypnotized about that 0.05. That's just an artificial threshold, okay? Could be any value. If something is very, very important, I will set up the sensitivity to very, very, very low. But if something no big deal, then any value is fine. Okay, next, we always said that, the experiment is normally distributed, right? I asked you guys to generate the noise, it's a bell shape, right? The next question we're going to ask is, how did you know this whole thing is normal? Okay, first I'll show you a QQ plot way, and then I'll do a SW test way. Okay, the Shapiro-Wilks. Okay, first about the QQ plot. How many of you ever heard QQ plot or PP plot? Never? Yeah? And what's QQ plot? Huh? Yeah, it's in a statistic class. Okay? What does that mean? Let me see if I can find a... I'm not going to use Wikipedia to explain, but I need to use their plot to explain. Okay, Q plot. This is a bad plot. Let me see if I can... Oh well, let me find a different way to explain this. Okay. Hey. Okay, people, suppose, okay, I have a bunch of number. Let me do it this way. Okay, from negative 0.001 and equal to this by plus 0.05. Okay, so suppose I have a number, a bunch of probability like this, and then if I want to plot it by normal distribution, norm, yeah, just standard normal. No, standard normal inverse. Okay, of this. And people, if I plot this, okay, first let me plot the other way around. Okay, if I plot this, how's this plot going to look like? Since it's a standard normal distribution, how the plot going to looks like? Huh? It's going to look like this, right? Right? If the z-score is below negative 3 is this way, and gradually the probability increase, and when your z-score around 0 is 50%, if above 3 is 99%, right? This is your Lean Six Sigma, agree? Now, if, okay, imagine this. I have a scorecard like this, and then I have another one. Okay, let me just do this. Control C. Okay, I'm plotting this guy, okay, and then I have another set of observation. What can I do? Maybe this way. Page special. JPEG. Okay. And then what should I kind of do? Can we flip this? Can we flip the picture? Huh? No, that's, yeah, here we go. Okay. Okay, now this is what I'm trying to show, okay? So here is a normal distribution from ideal normal. And here is a, say, data from an experiment, okay? So at the beginning, when your value is very, very low, my value is very, very low probability. When you reaching 0.5, I'm reaching 0.5. When you reaching 1, I'm reaching 1. So if I want to correlate them together, okay? If I want to correlate these two things together is to saying that when you're low, I'm low. Huh? How come? Oh boy. Here, if I'm trying to say that here's one observation, very, very small, and you're very, very small. I have one value, you're medium, I'm medium. Well, I have one value, you're high, I'm high. Then theoretical value versus the actual value are corresponding perfectly. Then I can match them with a perfect line, right? And that line is what? From your quantile to my quantile. Okay? Here. I guess I'm just saying. There can be a line like this, and this line is saying when your percentage is high, my percentage is high. When your percentage is 0.8, my percentage is 0.8. Then your probability and my probability almost one-on-to-one map. That is called PP plot. And then on the other hand, I can have one here showing that when your quantile is low, and my quantile is low, when your quantile is in medium, I'm quantile medium, and then that plot, quantile versus quantile, is called QQ plot. Okay? So usually, okay, we deal with the QQ plot. So the things you do is this. Let me show you the procedure here. Okay? If you understand the PP versus QQ, first, okay, you have a bunch of observations, and let me try a new one here. Okay. Young man, tell me how many random error term you want to have. 16? How many? 16? Okay, let's just have 16 error term. Okay, step 1, let's just have 16 error term. And this time, let me have the random error term in normal distribution. So I'll say normal SINV. Okay, so step 1 is not simulation. Okay, I'm lazy, so I'm using simulation. So I will have all the random numbers of the observation. And if I don't want to use this, I can have a mean value and standard deviation. But basically, I can have 16 error terms. Agree? The 16 error term is the regression error term, the pure error you got from your experiment. Okay? So step 1, you have your 16 error term. Okay? Pay special value. Lock your 16 error term. So far, so good? Step 2, okay? Rank. Your 16 error term. So data sort. Okay? Just continuous. Okay? And from the smallest to the biggest. So now we have our error term rank from the lowest gradually to the highest. According to the ranking. Okay? We just said that here is the smallest value. And here is the second smallest value. Oh. Okay, so I have 16 value here, agree? And then I'll say that if the 16 number are from a perfect normal distribution, how likely this value is from certain probability. So you will use your rank, okay? You should minus 0.5, not minus 1, because we're basically try to just, if you minus 1 is 0, and normal inverse 0, you cannot get a value. So now you have the rank. So probability-wise, what you're saying is that where I'm going to have my smallest error term, probably around 0.3 something. Where I'm going to have my largest error term, probably about 0.98 something. So now you can plot, okay, this and this. But one way to say that is that, now let's not plot the sequence. Let's just say that if this thing is really, really from a normal distribution, what will be the probability? So the probability of this thing is what? Normal normal distribution. No, normal standard distribution. Okay, and then normal normal SINV, because I need to find a quantile. Okay, so so now the way you can double check this quantile is that you know that somewhere in between here is 0.5, right? Right? And if it's around 0.5, what will be the probability? If it's perfectly normal. It's about 0, right? So you can tell it's almost 0. So now, what is a QQ plot? Is basically plot, okay, the relationship between your observation versus the theoretical normal distribution. And put it this way, if this guy is perfectly normal, just like our normal is supposed to be, this thing should be what? Hey, I'm low, I'm medium, you medium, I'm high, you high, then should be a perfect straight line. But if it's not a perfect straight line, it means what? Something is a little off. And so for me, actually, I know people write the report just say that, oh, I have the QQ plot statistics. I don't like the QQ plot statistics. A lot of time I like to look at the real plot. Because when you look at a real plot, for example, in this case, okay, it's pretty intense in the middle. I agree, right? Because the bell shape in the middle, you have a lot of more observation. You have less observation on the the positive tail and the negative tail. But in this case, can you guys tell, is the positive give me troubles or negative give me troubles? The positive give me troubles. So if, I'm the one trying to say that, hey, I work for CDC, you show me some experimental design for the COVID booster shots, and I see the plot here, immediately I'll say, hey, show me your outcome, experimental procedure, and your lab log. I'm more interested in where the things bend, because theoretically this 2 points should be a little higher to keep it straight, right? Yeah, so for me, just like if you take my reliability or survival analysis, my thing a lot of time is, nah, don't just give me statistics. I want to know why. How did this happen? This is beyond my expectation. I would like to know, is anything fishy there? Okay? And then, of course, when you've done this, you can just say that, okay, give me a correlation coefficient between the two sets. Because if the two sets are perfect, the correlation coefficient should be what? Very close to 1, right? You low, I'm low, you medium, I'm medium, you high, I'm high. So you will run the correlation coefficients between the experimental error versus the expectation of the experimental error, okay? And in this case, 0.97 is not too bad, okay? And in the test, okay, they actually show you that for different range, okay? And what we did is 16, right? So a little bit above, okay? And then, so no matter I'm using 0.01, 0.05, or 0.110, I would say that for 16 value, the value should be somewhere in between 0.15 and 0.12, but our value is 0.97, way above those values. So I'll say that I'll accept this experiment, the value is normal enough. And you guys know why I did that? Because remember, when I generate my random number this time, I intentionally use normal distribution random number. So, if this value is not significant, then something wrong with Excel. You follow me? Observation is normal. Threshold is normal. The correlation coefficient should be normal. And if the correlation coefficient is normal, the QQ plot should be, I'm in low quantile, you in low quantile. I am medium quantile, you in medium quantile. I'm high, you high. Then that should be a straight line. And if it's a straight line, the correlation coefficient should be 0.95 596 something. Okay? So this is a QQ plot approach to find a normality. So far, the legal test we cover, Durbin-Watson for what? For autocorrelation. Is your history bothers you. Bartlett test for equal local variations, equal space. You shouldn't have one subway station got a lot more local range of travel than the others. And the third one, QQ plot, is, hey, is all your random number or your error term is normal, okay? Yeah, and for the coming test, I already, I can tell you guys that the error, the random number I give you, you probably need to check if it's normal or not normal. Okay. Next, the Durbin-Watson, the QQ plot approach, people usually call it parametric approach. And then there is a so-called Shapiro-Wilks for normality, and this time it's non-parametrics. So the first things you do is compute the denominator of the D statistics, and how you come up with that is using every, time up?
5 minutes.
Okay, read this example 3. I'm gonna go through the numerical examples step by step next time, okay? But read through them. What I have in mind is, I still give you a little bit of homework to prepare for your exam 2, not to just, a large homework, but because you have a lot to study. And when you guys want to do the, I know several people say they want to have a review session. When you want to do that? Did you survey?
No, once the exam dates are finalized, I want to take.
Okay, yeah, figure that out. We can do that maybe after Monday or after class. We'll find a different classroom because Dr. Bai needs this classroom. Okay, and the review session is basically you can ask me anything except I won't tell you what will be in the exam.
Can we have a Zoom session?
Would you be there?
Yes.
Yeah, if you can help me set up a Zoom, I'll let people ask questions through Zoom. The only things I would say is this, okay? I give you my extra time, right? But be fair. I hate when one student try to dominate the entire review sessions and let other people, I think everybody should get a chance to ask something. Okay, so if you ask one question, I answer your questions, I would like to give other people a turn to ask questions. It's not fair, one person dominates 30 minutes of the review, okay?